So good afternoon, everyone. We are going to continue our seminars in statistics and data science. Today we have Dan with us. Daniel Jeske is a professor in the Department of Statistics at the University of California in Riverside in the US, where he served as the department chair during the 2008-2015. Is also a vice provost for academic personnel at the UCR, and previously was vice provost of administrative resolution. He is an elect fellow of the American Statistical Association and served on the board of directors between 2014 and 2016. He is the current president of the International Society for Business and Industrial Statistics, a society of the International Statistical Institute, and is also the past editor-in-chief of the American Statistician. His research interests include classification and prediction methodologies, statistical process control methodologies, biostatistics applications, and reliability modeling. Dan, it is a great pleasure for us to have you here with us. It is just a pity that you are in California and not in Brazil, but I think climate-wise, we are not that far apart.
No.
So thank you very much, and the floor is yours now.
Thank you, Paulo, for that introduction and for the invitation to talk to your department. And thanks everyone for joining. Okay. I think maybe my slides are being shown now.
Yes, they are.
Okay, great. So I'd like to talk to you today about basically an interesting problem regarding sample size calculations, which I think are very interesting in general. I think if somebody's really good at sample size calculations, they must know a lot of statistics, because the models that underlie a lot of the sample size calculations can be quite sophisticated, and also you're going to get people interested in your work, because everybody wants to know, or most often everybody wants to know something about how many samples they should take to have an efficacious study. So it's kind of a nice combination of work that's interesting and also work that's in demand. I don't specialize in sample size calculations, but this particular problem happens to be one like that, and also involves mixture models, which I think are kind of interesting as well. So I would like to mention that I'm talking about work that is with my collaborator Weixin here at UCR, and one of my current PhD students, Bradley Lubich, also here at UCR. So to set the scene for what this problem is, when we think about a control group versus a treatment group comparison, like a simple two-group comparison, very often we're imagining that the treatment group, if there is an effect, has a response distribution that's like the shift of the control group distribution. The whole distribution that is governing the responses for the control group just gets moved over, maybe to the right, if there's a positive shift that represents the treatment effect. But I guess recently in some of the medical literature, we have come to know that sometimes the treated population isn't really characterized that simply. Because if you think about what a shift does, is it moves, I like to think of looking at the left tail of the control group distribution. A shift of that distribution for a treatment response will move that tail to the right in the same way that every aspect of the distribution gets shifted over to the right, right? So it's very kind of a simplistic way of characterizing a treatment response. And what we're finding, I think, with discussion around personalized medicine and individual sort of responses to treatments is this notion of you might have a treatment that you give to a group of patients, And there's responders and non-responders. And the non-responder kind of subset of those treated patients have responses that look just like they would look if they were given the control group assignment instead. So it isn't like their stochastic properties of their response change in any way at all. They're not being drawn from a shift of the control group distribution. They're actually being drawn from the same distribution that's modeling the control group distribution. And then there's the responders, which is like a subset of the treated group, actually do look like they have responses that come from maybe the shift of that control group distribution. So the numbers that I've referred to here on this slide are papers in the literature that talk about this phenomena, and you can see it's around this idea of personalized medicine and also cancer trials, where we know the same kind of cancer therapies don't work for everybody, and there has to be sort of a customization to the cancer treatment for different people. So that's kind of what I'm really talking about, is how we model the response distribution for treated individuals. And I really am thinking about sample size in that setting to get the certain power of the null hypothesis that there's no treatment effect. I'd like to have the arm sizes for the control group and the treatment group determined so that I can detect a mixture distribution as the alternative to the null. So here's a picture that's a little bit more graphic of what I'm describing here. And if we were in sort of like the classic setting, we would see maybe a distribution like this one. The black one is the control group distribution, and then a pure shift is this green distribution. We'd say that's what we think we might see from the treatment group, and that shift size is delta. But what I'm really showing on this picture isn't the distribution for the control group and the treatment group. I'm showing what we actually think will happen from the treatment group only. And by that, I mean that in the treatment group, there's going to be a percentage of the people that are non-responders, 1 minus theta of them will come from this black distribution, which is the same as the control group distribution. And then a proportion theta of the treated patients would actually come from this shift of the black curve of size delta. And then what you get for the treatment response distribution is this mixture where I've just plugged in like 70%, 30%. So you get this kind of mixture distribution when you see the data from the treatment group. Now, of course, it's not going to always be this distinct that it's a mixture, right? Because you can, depending on what delta is and depending on what theta is, your distribution doesn't necessarily have to have two modes. It can have just a slight tilt to the right and be skewed in that way. So I'm sort of drawing a more obvious kind of mixture here than what you might see in practice, but this is the point here is that there's kind of like two components to the treated response distribution, and one of them is exactly the same as the control group distribution, and then the other one is a shift of that distribution. So here's now getting back to the sample size problem. Here's some motivation for what I'm talking about today. Suppose that a researcher wants to have a 5% Wilcoxon rank sum test, and they want 80% power for detecting a treatment effect that's a shift of half the standard deviation. So this is the classic problem, right? The way we would teach it in our classes, like, help someone figure out how many samples they need if they're looking for a pure shift treatment effect that's half the standard deviation of the control group. And you can work through the calculations, and this graph here, I'm going to refer to it, tells us, because theta equals 1 when we have a pure shift. So when theta equals 1, I'm going to get my sample size from the dotted line here, and it says it's like 50, 53. And then the power for my sample, for my design, is the solid line over here is 80%. So just look at this point here, 80% power I need 50 samples in each arm. What this graph is showing is what happens now to your power as theta slides back away from 1.0. So if I designed it this way, thinking it was a pure shift, I'm going to be in good shape with 50 samples in each arm. I'm going to get 80% power if that's what nature actually delivers in the way of a pure shift. But if nature gives me a mixture in the treated group that only 70% of the treated patients are responders, then I can get to this information on this graph by going to 0.7. And I can see, first of all, my power is now the solid line here, is only 50%. So I've lost a lot of power. I don't have what I thought I would get, right? I thought I was getting 80% because I designed for a pure shift. If nature gives me a mixture where I only have 70% responders, I'm really only going to have 50% power to detect that with my Wilcoxon rank sum test. And what I would really need instead to maintain 80% power is 100 patients. So I'd have to double the sample size in each arm, the arm size. I'd have to double it to maintain my 80% power if nature is really this mixture. So that kind of tells you the impact of using these mixture distributions as the treatment response. And kind of what I'm talking about today is how to figure out what these sample sizes are, and then bring that into the conversation with your collaborators on when they're sitting down before they, hopefully with you, before they start their experiment. They would ask you, like, what do you think I should have for my arm size? And then how do I go about estimating my treatment effect? We'll talk about that too. I just want to calibrate the kind of formal structure that we're using for this test, and that is the Wilcoxon rank sum test. So, and I was trying to be non-parametric, and that's why I chose that one. So, you know, in that setting, we have observations from a control group, our X's, and we have our Y's from the treatment group, which come from some distribution G, and the X's are from F. And then for our Wilcoxon rank sum test, we rank the Y's, find out what their ranks are when we pool the data. So we put all the data together, and then we see where the Y's slot in to get their ranks, the R vector. And our rank sum test statistic is the sum of those ranks. And we can test the null of no treatment effect versus the alternative. And to do that, we have this asymptotic test where we standardize the Wilcoxon rank sum statistic. And we know this works pretty well. This is a beautiful result from non-parametric statistics. And it's asymptotic, but it doesn't require enormous sample sizes. We just need to maintain this ratio lambda, which is the kind of the proportion of observations that are in the treatment group. Often this will be a half because we'll have a balanced sort of case, and lambda would just simply be a half in that case. So that's our, then this is distribution free. This is a result that holds no matter what F is, that the null distribution of the standardized test statistic is normal 0, 1. But we also know a lot about how W behaves under alternatives. It's a little bit messier, but not really intractable at all. We just have to compute. Now, of course, it's important to note right off the bat, though, that when we're talking about the distribution of W under the alternatives, we have to say what the alternative is. There is no distribution-free theory for what the alternative distributions are. It will depend on what you pick for the alternative. So you're going to have to calculate the probability that an X is less than a Y, and then these two, psi 1, psi 2, are related to the same X being less than 2 Ys. And here it's like the same Y being greater than 2 X's. You have to compute those things, and that's going to require some specification of what alternative you're talking about is. But if you arrive at those constants, then you can standardize W in a slightly different way and get a normal distribution that involves those constants, psi 1, psi 2, and the lambda is just that proportion of observations that are in the treatment group. And mu W here is the mean, and that's where gamma comes in. So that's really what we need to compute the power of the Wilcoxon rank sum statistic for some G, right? This is what's nice about this result is that you don't have to confine yourself to a particular family of distributions. You can just specify a G, which is different from F, and then you know what the distribution of W under that G is. And this is the critical region we defined on the previous slide for the Wilcoxon rank sum statistic. If we use that as our test, then that test has this power, that's asymptotic power. And it depends on the alternative that you chose through the psi1 and psi2 constants and gamma, the things that we computed up here. So then in practice, you could pick your M and N to make this power equal to 80%. And then that's how you would sort of design your study. Now, so what I'm talking about here today is picking a particular type of G, the one I started out motivating, which is that my G, which is the distribution that governs the responses for treated individuals, I want that to be this mixture where I have a percentage of the individuals theta responding, and their response is a shift of F of size delta. And then the rest of the treated patients, 1 minus theta is their fraction, just have draws that come from the same distribution as the control group. And I'll leave F open for the moment. So I have here sort of a 3 dimensions to what the model is. I have the F, which is the underlying sort of distribution for control group and non-responders. And then I have the treatment effect. And so now we begin to think about the treatment effect not just being a shift, like it might be in a standard sort of textbook case, but our treatment effect is also the percentage of treated individuals that respond, so it's theta, and then correspondingly how their response distribution gets shifted relative to the control group distribution. So now we can work through the power calculation. Notice that these constants now, we don't have to say they depend on G anymore because G is now specified this way as depending on F, theta, and delta. So all of the constants that we need to compute power are just functions of theta, delta, and F. And if we work through what do we need to do to make our power of the Wilcoxon rank sum statistic 1 minus beta, we'll find that we need these as the arm sizes. So you would just calculate psi1 and psi2 for your specified alternative. Now, and I do want to point that out that we know all the time, right? When we do sample size calculations, we have to insert values for parameters that we think might be the case, right? It's a design, right? We're not saying that that is the case, but we're taking this principled approach to designing our study so that it has a good property. Namely, if the alternative is this or close to this, we're going to have good power, right? So we would choose a theta and a delta and an F and calculate psi1, psi2, and gamma, plug them in here, rho just being this ratio of sample sizes, which we would often take as 1. We want balanced case. And then, so then we have our answer, we have our arm size to give us that kind of power. So I'm going to show some tables to indicate how that looks, but just wanted to mention a couple other things here first. One is that if I take this F now to be a location scale family, then it has this form where phi is what we could call a kernel, and mu and sigma are location and scale parameters. So if we had like normal distribution, for example, phi here would just be the CDF for a standard normal, right? Because we're centering here. And so as long as F belongs to this location scale family, we can say further that the power instead of depending on the F, theta, and sigma, now it just depends on this standardized kernel. Still has theta in here, but now K, where K is the ratio of delta to sigma. So we get a little bit more simplicity in the way the power depends on some of the characteristics of this treatment group distribution. So I'll be talking about location scale choices for F in the rest of this talk here. But I also wanted to mention one other thing too, is that we know also that the Wilcoxon rank sum statistic is a special case of a more general class of rank statistics, where instead of summing the ranks, you simply, like we do with Wilcoxon, we just sum the ranks of the Y's among all the data pool together. Well, you could do something more exotic and take functions of the ranks and sum those. And that's a general class of what's called linear rank statistics. And the Wilcoxon statistic just chooses the identity function. But we know that for pure shift alternatives, as an example, you can find more optimal scores. So in other words, you can get the same amount of power for a little bit less number of samples if you choose the so-called optimal scores, the A function here. And here's what that is. It's something you have to compute, but it's often not so hard to compute. It looks more daunting than it really turns out to be in practice. So I'm going to mention a little bit about, mostly my focus is on the Wilcoxon rank sum statistic, but I do want to give you some kind of comparison with what would happen if you were actually going to use some of these optimal scores instead. Because one thing that I can say here is that even though these are optimal scores in pure shift cases, they remain so in the mixture setting. So the same optimal score formula that was developed a long time ago for these pure shift G's, that same formula will work for this particular mixture that I'm looking at here as well. Okay, so let's look at some calculations and see how this manifests. So what I've done here is I've chosen the kernel to be this standard normal distribution. And I am looking at the balanced case. And so then, because that's the location scale, my power only depends on theta and then delta over sigma, what I was calling K. So I have a table here that shows a range of theta and a range of K that you would probably talk through the person you're trying to help design their study. And you know, all the time that we do sample size calculations, we show a variety of options, right? Where we show sensitivity to the choices that you have to make about the parameters that go into power studies. And they trade that off with how much budget they have for the samples. So it's a conversation that you have. And I'm really talking today about expanding the scope of that conversation to, instead of just talking about a shift size and maybe a variance, I'm just saying, well, we really have a shift size, a variance, but also a mixture parameter that we need to talk about. And actually the variance kind of gets blended into this K, right? So in the classical problem, you would measure your shift size by some multiple of sigma. And then you don't have to worry about sigma, right? Because if delta is some constant times sigma, then the sigma cancels here, and you're just talking about that multiple for K. But anyway, what you see in this table is a variety of options. And let's start here, where I choose theta to be 1 and K to be 0.5. And do you remember in my motivation slide, I talked about that graph in the lower left corner of the slide. And I said 50 samples gives you 80% power. That's this number. And that was the case where I had a pure shift and I was looking for 0.5 shift relative to standard deviations. And then I said, and guess what? If that mixture was now 70% only, you had to double your sample size. So it went from like 50 to 100. That's this cell. right? So you can see that as you work your way back, you're getting these increasingly larger number of arm sizes to maintain 80% power for your Wilcoxon rank sum test. And obviously, the smaller this shift for the responders is, the bigger your arm size has to be, right? And that's really a very small shift, right? Most of the time we're talking about like 0.5 or 1 or 2. We hope that our treatment has a more significant impact than 0.25, but it's interesting to see what those numbers look like. And then I wanted to just draw your attention to something that might help you kind of remember what these tables say. If you look at the bottom row, which is the pure shift case, and 0.8 it's about 1.5 times bigger than the bottom row, right? Just to give you a feel for how these numbers change. All these numbers are like 1.5 times all the numbers in blue. And the very top row is roughly 4 times the numbers in blue. So you need somewhere between 1 and 4 times more samples across this table to take into account your non-responder and responder kind of mixture for the treatment group. And the other thing I wanted to show is the numbers in parentheses here. Those are what you get if you use those optimal scores. So you can see there's not really a tremendous difference between the Wilcoxon rank sum test and the optimal linear rank sum test. And another feather for the Wilcoxon rank sum statistic, right? It's not the optimal one, but it's very close to giving you the good performance that the optimal one does. And then also, I wanted to compare like what other non-parametric tests might I use in the case of F equals G versus F not equals G. Well, of course, the Kolmogorov-Smirnov test is one of those. But we know it's perhaps so general, so omnibus that you pay a price for it in power. And we can see that if you use the KS statistic for these sample sizes, you're not going to get your 80% power. You're going to get something closer to 68 to 73 as a range across all these designs. Okay, so then a couple more tables that are very similar. Here's now where I changed the kernel to logistic. So here's the formula for the kernel now, logistic. And it's a standardized kernel. So this C just makes it mean 0, variance 1. And there's no parentheses here because the optimal scores in the case of logistic are in fact the identity function. That Wilcoxon rank sum is the optimal one if the underlying F is logistic. Again, you can see roughly this is 1.5 times that one. And this top row is like 4 times that. And if you look, you'll see that compared to the normal, all of these numbers are a little bit smaller. Here's the normal, like we have 836 and 581, and here's 731, 507. All of them are a little bit smaller than the normal if we use this logistic kernel, and still we see the Kolmogorov-Smirnov as a little bit closer to 0.8, but not there. And then here's Laplace, still smaller, right? Because we had here 731, 507. Now we see 546, 379. So a little bit smaller still for Laplace. Still that 1.5 ratio to the bottom line here, and still like 4 to there. There's something there going on. Kolmogorov-Smirnov test, variable. Sometimes maybe a little bit better, but often worse. And then here's a T with 3 degrees of freedom, and still smaller, right? Because we've gone now 546, 379, 428, 297. So I remember it kind of puzzled me at first, like how come normal, the most friendly distribution of all, probably, right? Why is it that gives me the biggest arm size? Not that there's anything wrong with that necessarily, because in a way, if you want to be conservative, at least relative to these 4 distributions, you could use the most friendly distribution, right, for your design alternative. And again, we're not really saying that we know for sure that nature is going to give us one of these distributions. This is a choice we have to make to have a principled approach to getting an arm size calculation, right? We have to choose something. We have to have some structured reasoning to get a sample size that we could kind of hang our hat on and say, you know, that makes sense. And if I look at this as a set of alternatives to choose from, I could say, you know, I don't mind being conservative here. It's insurance against a bad assumption to have a little bit more than I need. So if I was looking for, you know, a 1.0 shift and I thought theta was 0.7, yeah, and if I believe that this sort of heavier tail distribution T3 was a good kernel, standardized, I could go with 19, or I could say, well, on the other hand, Laplace is 24 and logistic is 27 and normal is 30. Why don't I just do 30 if I can afford it, right? Because then I can have at least 80% power for all four choices. And 30, you know, okay, it's more than 19, but maybe I can afford that, right? But anyway, this is the kind of conversation that you would have when you're trying to help somebody design their experiment. Now, why does that normal have the largest one? So I did have to think about that for a while. And I came to this understanding that why don't I try to look at it from the standpoint of how far is the alternative from the null in these four cases of T3, Laplace, logistic, and normal? How far are the hypotheses apart? So I use callback-Liebler distance to measure the distance between the null and the alternatives. And each of these graphs is a different theta. Let's just look at this one here. And then what I have here is K, and I'm plotting for each of the four distributions what the callback-Liebler distance is between the alternative and the null. And you can see that in each case, the blue curve is on the top, and the black curve is on the bottom with green and red in between. So they order themselves in every one of these panels the same way, that the distance between the null and the alternatives for those distributions is the highest for the T3 distribution, standardized, the standardized T3. Remember that, and I think that is important, right? Because you might be thinking like, how can this be, right? The T3 has a variance that's 3, right? It's like degrees of freedom over degrees of freedom minus 2. So T3 has a variance of 3. It's much, much heavier tails than a standard normal. And that's true. But I am standardizing the kernel in my formulation here. So they all have mean 0, variance 1. And after you do that, you get the distance here between the null and the alternative to be ordered in precisely the way that intuitively it makes sense, because the further away you are from the null, the fewer samples you need to detect it, right? And that's what we were seeing with T3. And the normal being the closest to the null, well, that's a more subtle change then, right? If it's close to the null, so you need more samples. So that's how I came to kind of feel comfortable with this. So now we come to, once we have run our experiment, we have our data, we want to estimate the treatment effect. And in the pure shift case, what the treatment effect is defined as just the difference in the two means for the treated group and the untreated group. But in a mixture setting, it seems like really when we have a two-dimensional treatment effect. We have this component that describes the mixture pieces, theta, and then we have the delta, that's the shift after you identify responders. So we looked at method of moment estimators here. You can, if you denote the variances of x's and means and variances of x's and y's this way, you can develop this mapping between mu f sigma f squared and mu g sigma g squared in terms of theta and f, and then also delta, right? Delta being the difference in the two means. So with that, with these formulas here for what theta and delta represent, now you can just plug in your estimates of these. Sigma g squared is just sy squared and so on, right? And delta is going to be y bar minus x bar. And we use the positivity part here because we know that sigma g squared is bigger than sigma f squared. We know that, right? Because anytime you have this mixture of f and a shift of f, you're going to get more variance than f alone. And likewise, the mean is bigger. So we put in this plus sign here as positivity. And also in these denominators, we added in an epsilon n to keep the denominator from being 0, which it could be because of the positivity piece, or otherwise just being some really, really tiny number, which could cause problems when you divide by it. And we wanted an epsilon that would go to 0 as the sample size gets large to preserve the consistency of the estimators, because with these as the estimators, we can show that they're consistent and asymptotically normal. So we have this result here about each of those two estimators behaving nicely. And the asymptotic variances, they're a little ugly to look at, so I'm not writing out the terms here, but they aren't that difficult to develop. It's just harder to write them down in a nice way. So I'm showing the leading terms, but there's a few more, 2 more terms in each case. With these results, we could look at properties of them in terms of mean squared error and even construct confidence intervals from them. So looking at bias and mean squared error first, this table shows for different choices of f, theta, and delta, and then different sample sizes, what happens to bias and mean squared error. So the yellow columns are biased. Let's look at those first. And we can see as we move from left to right, increasing our sample sizes, that the bias does decrease as we would have predicted it to based on the consistency. And so does the mean squared error if you look at these white columns. And nothing, I don't think, particularly striking about the difference between the F's here. And this is for theta. And then we have the same thing for the estimate of delta, where the bias is decreasing and the mean squared error is decreasing. So they're behaving the way we would have predicted them to behave. But now, what about the asymptotic normality, and can we utilize it for some large sample confidence intervals? So here's a picture that illustrates the rate at which these estimates converge to normality. We do know they do converge, but we don't really know how fast yet. So the top row here is theta hat, the bottom row is delta hat, and we're showing how much these histograms from some simulated data look normal, and looks a little rough here at 25, gets a little bit better at 50. Similarly for delta hat, and then when we add a couple more sample sizes, 100 and 500, we see that it is indeed verifying the theory of normality. And maybe we also see that by the time we get to between 50 and 100, the intervals look fairly decent. Sorry, not the intervals, but the approximations to normality look fairly decent. And then we could maybe use those to construct confidence intervals for theta hat and delta hat, just using the normal percentiles here, Z. So if we do that, here's what some of the numerical work looks like for that. This is a confidence interval for theta, nominal 95%. Again, our choices of F, theta, delta, and sample size. And I've highlighted the yellow ones as ones that are a little bit far away from 95%, maybe too far away to think that it's wonderful. So if you don't see yellow and we see it disappearing as the sample size gets big, these are all within 0.02 of nominal. So they're 93, 94, 95, 96, 97, right? All of them. So that's pretty good, I think, in terms of reaching the coverage. And we see that's happening again, between 50 and 100 for theta. a little bit more of a struggle for delta. I don't quite understand that yet, but we do see the yellow hangs around a little bit more. And, still isn't horrible, right? It's 98 instead of 95. So, and they seem to be mostly conservative. There is a 94 here, but that could be Monte Carlo error also. So it seems like the intervals, if anything, they're probably a little bit conservative. We saw, some 96s, 97s, but here we did see some 93s. So for theta, maybe it isn't really as pronouncedly conservative as it might be for delta. Yeah. Okay, so in sum, I guess what I've tried to talk about here today is a power calculation that tries to get a little bit closer to what we think we might expect to see for a treatment distribution. Instead of it being a pure shift, it's a mixture of that control group distribution and then a shift of that control group distribution. And that's based on this idea of responders and non-responders that we see from some of the medical sort of applications. And one of the bottom lines to take away here is that if you do that, if you power your study this way, you could expect there to be larger sample sizes. And we illustrated that with some of the tables. And then we talked about a way to estimate theta and delta using method of moments, and looked at ways to get confidence interval procedures based on large sample size. Now, we are still trying to think about other options to estimate theta and delta by. I wanted to tell you one of the things I'm thinking about right now. I haven't really solved it yet, but I feel like this might be a good path. So I thought I'd roll it out here and see if anybody had a comment about it. But so the underlying problem here is, you have observations that come from some F. I was calling it phi in the talk here. And then these are your control groups, right? Control group data. And then you have your treatment groups, observations, which is a mixture of that thing and a shift of that thing. So here's the U minus delta part. So now, in some ways, I would like to be able to utilize information in X's to learn about phi and mu and sigma, right? Because this is, you could sort of think of the Y's stars as being contaminated data, because it has information about phi that's noisy in some sense, right? Because you've got two components of it. But X just gives you pure information about phi and mu and sigma. So we could use, for example, X bar and SX in place of mu and sigma, and center our data and scale it, both the X's and the Y's with mu. And if we do that, we get sort of maybe you could say a canonical form for the data. So the X's now just are straight away from this standardized kernel. And the Y's are a mixture of that standardized kernel and a shift of that standardized kernel lambda, which is this ratio. So it's a simpler setting, right, where I just have a ratio lambda and a parameter theta, and then there's some underlying kernel, which I could learn about from the X stars also, right? If I just look at the Xi's here and standardize them, it tells me everything. Well, not everything, but it tells me a lot about this kernel. So there's information in different places. So my thought was that if I'm trying to learn about theta, what I could do is look at the ranks of the Y's and see how many of them are mixed in with the X's, right? If we think about the Y's, some of them look like X's and some of them don't, right? If we have a strong effect for the responders, those Y's will be way over to the right. But then the non-responders, they'll be a lot like the X's. So that kind of gives you information about what fraction of the Y's mix in well with the x's, that could almost be an estimate of 1 minus theta, right? Because, I mean, we have to, in order to make this a little bit intuitive and concrete, we have to think about a big shift for the responders. So you have all these y's, a fraction of them are going to look a lot different from the x's. And that tells you something about theta, right? That fraction is theta. Now, of course, it gets noisy if the delta isn't very big, right? That maybe just for intuition, think of it as a simple case. And then with regards to delta, it's like how deep the y's are inside the x's tells you something about delta. So I was thinking, and this is what I'm working on now, is that I could look at what's the probability that a y is less than or equal to an order statistic, the rth order statistic amongst the x's. And you can work this out to some degree and get 1 minus theta r over n plus 1 plus theta times phi of the quantile of phi, the r over n plus 1 quantile of phi minus lambda. So what if, I'm thinking now of a least squares estimator, a nonlinear least squares estimator. So I'll define SR to be like how many of these y's are actually less than XR. And SR over n then would be an estimate of this probability. So I could do that for each r and then look at the square deviations between observed and model-based answer. And so it's a nonlinear least squares problem, which, I don't know, seems to me like I have a good chance of solving this one. There's only two unknowns, theta and lambda. Now the phi, I have to put something in for phi. That's true. But my hope is that maybe the least squares estimates I get this way, whether I put in phi for normal or phi for Laplace or phi for logistic, these are all standardized kernels that maybe it's not so sensitive to that. Compared to like if I went full bore with maximum likelihood, right, where I have to use everything about the distribution. So my hope is maybe that if I can estimate theta and lambda hat this way, I can get a robust estimate of theta and lambda relative to like a fully parametric maximum likelihood approach. But I haven't worked on this enough yet to know if that's going to work out. But that's kind of what I mean when I say ongoing work to look at other possible estimators of confidence intervals and so on. I'd like to stay as non-parametric as possible, but might have to give up, completely non-parametric. Like method of moments, everybody wonders about, like, really method of moments, but they are fully non-parametric, right? That's very nice property of them, and they don't work too badly. But yeah, I'm kind of interested to see if I can, get some better estimators. That's kind of where I am now. All right. Well, thanks. That's what I wanted to talk about today, and I'll try to turn it back over to the room.
Thank you very much, Dan. It was a very nice talk, a very important topic. I can now open the floor for discussion. If you have any question, it can be either in Portuguese or in English. I can translate it if needed.
I'm glad you will, Paulo, because I
yeah, otherwise we have a problem of communication. Paulo is congratulating you for the excellent presentation. I have a question more in a practical way. So do you think, because often we have when we discuss with colleagues from different areas that want to do some kind of study, it can be this kind of studies or something else, they usually ask how many subjects they should have in their study. Do you think with this you can give some help on that, or could you translate those results for a practical application in that sense?
Well, I think it expands our conversation about that topic, because if we think about what we would do in the simplest setting, where we assume the data is normal and it's a two sample comparison, and the treatment is a pure shift of the control group, we have a sample size formula, right? It's like sigma squared times z alpha squared plus z beta squared over delta. And then we would lay out a table where we'd say, if sigma is this and delta is this, here's how many samples you need. So I think that rather than that conversation, we could maybe take this and ask them first, do you really think that the treatment would be a pure shift? Do you know, like, there's non-responders and responders, and we could model that, and we could get a sample size formula too. That's what I talked about here, and show them that table. And the old case is one row in this table where theta equals 1. So I think the answer is yes, we can help them. And what I've tried to present is a way to do that in a broader framework. And the other way to help somebody with sample size calculation, I'm being a little facetious here, is there's a very, very simple formula for how many samples somebody needs. Simplest one ever. And it's the total budget that they have divided by the cost per sampling unit.
It's like, as many as possible, right?
Right. That's what,
yeah, usually then.
Yeah, but that might actually be very practical, but it doesn't have any principle to it other than spending all your budget, right? So I think we need to have some principled approach to it that you can hang your hat on and say, here's why this might actually be a good number, because of if the alternative is really like this, I'm going to get 80% power, and if it's something like some of these others, I'm going to get more than 80% power because I chose the normal distribution to be conservative relative to the Laplace logistic T3. So it just makes everybody feel better that it's what I keep thinking of as a principled answer.
Yes, thank you. Is there any question or comment? Don't be shy. I have a second question. I think you explained, but I didn't get it clearly. Why did you use T distribution with 3 degrees of freedom? Why 3?
It's the first one that has variance that's finite. So it would be the heaviest tail of the T3 of the T distributions that has a variance.
But if you have a higher number of degrees of freedom, will it improve or?
Now that's a good question, yeah, because I'm standardizing the kernel. So the shape is a little bit different, but if you standardize the T5, and actually, of course, the first answer maybe to that question is the more degrees of freedom you have, then the more it's going to look like the normal number.
Yeah, exactly.
Yeah, but if you stay away from degrees of freedom that are 25 or higher, and you say, what happens if it's a T5 or a T8? But because I'm standardizing the kernel, the difference will be pretty slight, I think. If you draw the PDF, they both have mean 0, they both have variance 1, because I standardized. There'll be a little bit of a difference in the shape, but not too much.
Okay. Clever raised his hand. Do you want to say something, Clever? Yeah, please.
Yes, I'm not good at English, but I will try to say something. I'd like to know, teacher, if there is any effort to make variance different, if there is any meaning for that, and it would be any effort to do so. Thank you.
So first of all, your English is pretty good and a lot better than my Portuguese. So. But so the variance, so I think you might be talking about like sort of the easiest textbook problem is where the control group observations and the treatment group observations all have the same variance. But sometimes the treatment group observations can have a different variance. And that's actually a famous problem in statistics, classical statistics, called the Behrens-Fisher problem. Because you know what, there's no exact test. There's very good asymptotic tests for like if the two means are equal from normal distributions that have different unknown variances. There's no exact test for that, and yet it is something that we sometimes wish that we could allow, right? Because why should the treatment group observations have the same variance as the control group observations? Well, in the setting that I described, we don't assume that, right? Because the mixture distribution actually results in variances for the treatment data that's bigger than the observations in the control group. It's what I do assume, and maybe that's really more your point, is I assume that the two components of the mixture have the same variance. I do assume that. And maybe I could someday relax that and not have just one sigma, but a sigma 1 and a sigma 2 there. But that is some complexity I haven't yet entertained.
Thank you. Thanks, Sam. Is there any further questions or comments? Thanks, Pavel. Okay, I think not. So if anyone has anything to comment or to ask Dan, you can write me, and I can give the email, Dan's email to you, and you can contact directly. Dan, thank you very much for your time, for your presentation. It was really a great pleasure to have you here with us.
I enjoyed it so much. Yeah, I look forward to seeing you all soon somewhere, maybe at ISBIZ or ISI or US or Brazil, somewhere.
Yes, let's hope ISBIZ is closer than the others. Yeah. Okay, thank you very much.
Thank you. All right, bye-bye.